We're now moving into an area of the class that you probably have never seen before as to how to solve these systems of nonlinear equations when we get to 4 precision positions. So in this video, I'm just going to do a quick overview of 4 precision position synthesis and talk about some different solving techniques and why we might choose one over the other. So first of all, taking a step back and looking at how the trade-offs go between precision positions and the number of free choices that we have. Remember that we can go from position 1 to position 2 or 3, and if we call that generically position J, we can then go up to 4 or 5 precision positions. So thus far we have started with 2 precision positions. We did this both graphically and then analytically. And in this case, we're prescribing a displacement vector for a motion generation case, displacement vector as well as the rotation of the coupler. And then I end up with that prescribed information. My unknowns are the link or the vector that's pinned to ground, which goes up to the moving pivot, the W vector, and then the Z vector going from that moving pivot up to the precision point. Those two are unknown, as well as the rotation of the input link, the beta 2 angle. So because we have one vector loop equation, that's the equivalent of 2 scalar equations, and we then end up with 3 free choices to solve this system of equations. We then spent quite a bit of time on 3 precision positions where we add another displacement vector, delta 3, and another rotation angle of the coupler, alpha 3. We added one more unknown, and so because we have an extra vector loop equation, equivalent to 2 scalar equations, and we only added one unknown, we end up with 2 free choices in this case. So the way that we made use of these free choices, we first of all started off by picking our moving pivot locations, and we did this graphically. And then we said, well, to make the system of equations linear when we do this analytically, we went ahead and picked the beta 2 and beta 3 value, and it made it very easy to solve it. And this is equivalent of motion generation with prescribed timing, because we're prescribing how much does the input link rotate as I go from position 1 to 2 and 1 to 3. The other thing that we looked at was using these 2 free choices up by placing our ground pivots, or selecting the X and Y location of the ground pivots. And we did that with that radius vector and went from the ground pivot up to the precision point. So what happens when we step beyond 3 precision positions? That's where we're headed today. So 4 precision positions, we add an extra vector loop equation, so displacement vector to 4 as well as alpha 4. And then we also add an additional unknown, which is the rotation of the link pinned to ground, the W vector, from the 1st to the 4th position, beta 4. And because of this, we're now left with 1 free choice. And regardless of how you try to treat this, it is going to be a nonlinear system of equations that you need to solve. But I think you can also imagine that we could add an additional position as well, go up to 5 positions, and now we have 0 free choices, and we're going to have a finite number of solutions. We'll talk about that a little bit later. So how do we solve a 4 precision position synthesis problem? We have 2 primary areas of solutions. One is Burmester curves, which we'll spend really the majority of our time doing, and the other is point precision reduction, which is basically forcing the moving pivot of our solution to be at one of the poles, and then this reduces it really from a 4 position problem down to a 3 position problem. And it's not very useful because you can only generate one decent solution with it. So we don't spend really any time with point precision reduction. But Burmester curves are an area that we spend quite a bit of time with. And we'll first of all start off graphically, and then we'll move into an analytical approach. And within the graphical approach, there is a purely graphical approach, which is called the opposite pole quadrilateral. Before having digital computers, this was very popular. It's quite extensive approach and not very easy. I don't find it particularly useful when our analytical approaches are very powerful. But we will look at superposition. And this is the idea that I'm going to take two different 3 precision position problems and superimpose them. So the first problem would have positions 1, 2, and 3. The second problem would have 1, 2, and 4. We'd superimpose those and find where do we get overlap between the solutions. That's our superposition. And then we'll also look at it from a complex number perspective where we generate our standard form equations and solve the nonlinear system of equations. So with this, our next videos will dive into actually doing the superposition and then going into complex number 4 precision position synthesis.